In this assignment, we will show how we can perform geospatial modeling of a landscape process using widely available GIS tools such as map algebra. After opening GRASS, let me change to map set for this assignment. I call it assignment 7. Feel free to create a new map set for this assignment. Then another step that we have done for each assignment is to change to the working directory, and where we will download all these text files, which include recode tables, color rules, and label rules. And I have already done it, so I will check whether I have all these files in my current directory. So I can, on Mac, I can check my current directory using pwd, and I can check whether I have the files there using ls. So as you can see, I have them there. And you can do this on Windows using the command dir. And then another step, what we want to do is open this brief theoretical background for GIS-based erosion modeling. And I already opened it here, because we will be following essentially this document in terms of the equations. So this document explains all the variables that we will be using, what kind of units we have for these variables, both the US units and international units. And then we will do the topographic erosion potential for universal soils equation and its three-dimensional version. And then we will use the unit stream power-based erosion deposition model, USPED, to compute first the sediment transport capacity and then net erosion deposition as divergence of sediment transport capacity. That means the change in the direction of steepest slope, in the change in the direction of flow. So now we are ready to get started. And in this first part, we will be computing the topographic erosion potential using this equation. And we will be exploring what impact does the choice of parameters M and N have on the resulting spatial pattern and values. So let's set the region to that small rural watershed. Let's compute the slope and aspect as our input, as the parameters that we will need later on. And as you have seen, the slope is one of the parameters in our LS factor. So this is the aspect. As you may remember, aspect also represents direction of flow, and this is the slope map. So we will use these two maps in the equations that follow later on. Then another variable that we will need in our equations is the upslope contributing area. It's here. And again, as we have done in the previous assignment, we use flow accumulation to compute our upslope contributing area. And because our resolution is 1 meter, grid cell size is 1 square meter, the flow accumulation is already a contributing area for each grid cell. So now we have upslope contributing area for each grid cell, and we have slope for each grid cell. So now we can compute topographic erosion for potential using this equation. So let's just run this map algebra expression, and first we will run it with the exponent m equal to 0.2 and exponent n equal to 1.3. So this is that exponent for the flow accumulation parameter and exponent for the slope parameter. And then we will put more weight on the flow accumulation and less weight on the slope. So this will be, we will have higher M parameter and lower N parameter, and then we will compute another version of this topographic erosion potential. And let's assign the color table, and you can see it's histogram equalized because we have a highly nonlinear distribution. So this is how that LS factor or the topographic factor for erosion potential will look for one set of the parameters, and this is how it will look like for the second set of the parameters. And you can see that, that the flow accumulation is more pronounced in one of them. So let's now to compare those two results, let's now create some clean output maps for our report so that you can look at them and you can comment on what you see in that spatial distribution. So let's erase all those intermediate maps. Now we will output one of the topographic potential maps. We will combine them with contours, and you can see that we have that high erosion along in those areas where the contours are pretty dense. That means this is the steep slope. So this output highlights the impact of slopes. So you should check what kind of parameters we used there. Let's include a legend. And this legend, let me try to put it here. With the flag -d, we include the histogram for that legend. So as you can see, there is like most of the values are really along this lower range, and there are only very few grid cells that actually have these extremely high values. And I will add the bar scale. Let's put it here. And let's save this map that has the slope parameter, the N parameter 1.3, so higher than the other ones, and this one stresses the slope impact on the spatial distribution of erosion. And then if we have soil and cover properties in such a way that we have a very strong impact of concentrated flow, then we have increased the impact of flow accumulation. And let's look at how that result looks like. And so we can see much higher erosion, much higher impact of flow accumulation there. So we have now a lot of erosion in those areas that are like these little valleys and little concave areas. let's include the legend, and I will keep the legend for the other one as well, just for comparison. And let's put this one here. So what you can see when you compare these, just these legends, that for this new result, we have much higher extreme values, but again, most of the values along this are along these lower ranges. So now you can, with these two results, you can answer the question about which equations represents conditions when contributing area has greater impact and when slope has greater impact, and which one result predicts higher erosion rates. So this was only taking into account topography. So imagine that this would be a situation when this entire area would be just bare ground, no spatially variable land cover. So we have purely impact of topography. But this situation is pretty rare. So we can now incorporate the land cover into our modeling through the C factor. And the C factor is an empirical cover factor that was derived from many experiments with different kind of land covers, and it's available in literature and in official tables. So we will take a land cover map and we will recode it. Let me just save this map. And what I don't have here, I don't have here the land cover map displayed, but you can easily do that. We can add add another raster layer, and you have to look for it in the permanent map set. So it is this land cover 1 meter layer, and let's just remove this legend, and we can add raster legend for this land cover. So I can make it a little bit smaller. Let's just put it here, but still so that we can read it. We are not going to save this. This is really for your information so that you can see what kind of layers we have here. We have paved road, dirt road, we have some surface water, we have forested area, and we have agricultural areas. And what we will be doing, we will be creating two scenarios or modeling two scenarios. One, when the agricultural area is bare, so it is off season, of growing season, and then when the agricultural area is covered with vegetation, with crops, so during the growing season. And to create the C factor maps that are derived from this land cover map, we will use recoding table, and that's this one, where you can see that, for example, for the forested area is number 2 category, and it has these very low C factor values. So that means that there will be very low erosion in these locations. The agricultural areas are, I believe it is the 8 or 7, so they have 0.5. And what we could have done in this legend, we can just keep those category numbers. So the agriculture was category 8. So that's what we are doing here with the r.recode. So we are converting our land cover map to C-factor map. Then we will assign it color, like a special color table that is similar to our land use map. And now, instead of these land cover categories, let's just remove the legend. What we are looking at is the C factor. And the C factor is between 0 and 1, and it just represents what is the rate of the erosion, or how does cover modify erosion. So if it is 1, that means that there is an erosion as much as a bare ground. If this C factor is lower, then it effectively lowers the erosion. So let's just modify this legend, put it into this place. So here you can see what kind of values we have assigned to these different land uses. This gray color, those have 0 erosion, and those are the built areas or water. So we can save this map for our report now. So now what we will do, we will now compute the soil erosion potential or soil detachment potential using this full equation, where this LS factor or topographic factor we have already computed using this equation. But now we will add the R factor, that's the rainfall factor. We will add soil erodibility factor that is taken from the soil database, and then we will add the land cover factor that we have just generated. And then there is also a prevention measure factor if we had, for example, some terraces or some other erosion prevention measures. So we will be using map algebra to compute it, and this 270, that's our R factor, that's the rainfall factor for the central North Carolina. Then I have already created the map for the soils erodibility map, and again we can look at it, how it looks like. I don't have it in the instructions, but it is in your permanent data set or permanent map set. Soils K factor. So this is how that map looks like. Let's look at the values. So you can see that we have the maximum is 0.28 in these locations, and we have 3 different types of soils in this area. So now we can compute this. So we have all the maps, and I have prepared this C factor. The one that we have recoded is for the bare conditions in agricultural areas, but there is also in the permanent map set a C factor data layer for the growing season, which just has the lower C factor for the agricultural areas. And you can display it just to check how it looks like. So let's just run our map algebra expression. So this would be for the scenario where the agricultural areas are bare. This is for the growing season. Then we use a custom color table or custom color ramp for displaying the soil erosion map. So this is how it will look like. So you can see this high erosion potential in the locations that are bare. Oops. And then we assign the same color table for the growing season output. So we still get higher erosion in those agricultural areas, but it is much less. So now it is really the dirt roads here that are producing the most sediment. And what we will do, this is a new thing that we haven't done before, is we can add to this map the units so that if we want to compute it in further modeling, or if we want to do some summary statistics, we have the units that are represented by these values in the database. So in our case, it's ton per acre per year. And that's really driven by the R and K factor. And we will add it also to the other map. And let's now generate the output maps for our report so that you can look at them and you can comment on the distribution of the erosion for these two different scenarios. So we will just clean up, then display one of the maps. Then we will add the legend. So let me just get rid of this one. Okay. So now I have those units with the legend, and I will put my legend here. And I have included the histogram with the legend. You can skip it if you want to. That's that -D flag. But I just wanted to highlight that most of the values are again in this very low category, and that's all of these green areas. So I may need to make it a little bit smaller. Let me do that. Now it is nice. Okay. And I need to zoom to computational region. Okay, that's better. And I can save this map. Now let's do the map during the growing season. And I will just add the legend. So you can see that I have now lower values overall here, and we can just save it. And we can also run statistics on our on both of these rasters. So for the bare ground, for the bare agricultural areas, we have much higher range of the erosion values. The mean is 8.6 tons per acre per year. That's really high. For the growing season, the mean is just 1.7. That's relatively stable. So we have saved this map. And then we will do net erosion deposition maps in the following video.